Hello and welcome everyone. So I say good morning, good afternoon, and good evening to wherever you're joining us here on the continent or outside the continent. So before we start the presentation today, I will quickly invite you again just to take a quick room temperature check. Go to menti.com and type in the code 81630254. Just one question. Just want to know where you're joining us from. Okay. Excuse me. I see 92 participants already here, and 5 have joined the Menti. So we're from South Africa, Nigeria, Kenya, Sudan, Zimbabwe. Okay. That's a good one. All right. Before we start this session today, this first live session in this 6th edition of our 0 to Certified IPv6 Engineer cohort or workshop, I, Olatunde Obili, one of your presenters today, would like to use this opportunity to apologize for the recent events that happened from the beginning of the 6th edition on Monday, 16th September. So we've been going through experiencing some technical challenges, which we've never experienced before. Like I said, this is the 6th edition, and we're learning. So each edition has presented new kind of challenges, and this is the first time this happened also. So, but anyway, we got down to business and tried to mitigate the effects of these different challenges we were experiencing. So one of the things we did was to switch off the automation that automatically on-enrolls students or learners who are not making progress within the cohort. We switched that off because if you remember on Monday, I mentioned it that there was an automation because it's not done manually that would do that. And then we got some emails and we also reassessed and decided to switch that off. And then again, we decided to extend the workshop by 1 week because the main technical challenge, you guys were facing, or ladies and gentlemen were facing, involved accessing the access speed. It was very slow. The website was very slow, accessing the learning management system or the platform. So we decided to extend the workshop by 1 week to make up for that lost time where learners couldn't access content when they wanted to access it. And then finally, I'm sure most of you got the emails yesterday. We decided to change the format because normally we used to do a live session like today, Friday. We would do a recap for everything you've covered during the week for the first week, for example, for this first week. So, but now we decided to change the format. And we did send a communication out to get some feedback from you. And we did see that the majority were comfortable with this format of Zoom live sessions, multiple live sessions to the end of the workshop. And I would like to use this opportunity to thank you for being very, very patient with us and sticking with us up to this very moment. In fact, when I saw the survey, the feedback results, from over 100 respondents, an overwhelming almost 90% chose to continue with this format. And with this, I, on behalf of the team, are very, very grateful for that. And we like you for, we appreciate you for sticking with us. And we're here right here at the live session right now, with over 100 attendees right now. So we thank you very much for that. So with that said, I hope you've forgiven us. I believe you have, and then we move on to the live session for today. So let me share my screen again, and then we'll see. Let's go there. So yeah, I see the results of the poll here. Nigeria, South Africa, and Kenya stand out a bit. So thank you, all learners from all over Africa. So, like I said during on Monday also, for us to have a very good user experience or viewing experience and learning experience while we are on this live session, There's some few house rules just to make it better for all of us. So at the bottom of your screen of your Zoom client, whether you updated it or not, you have the chat button. I mean, the chat icon, which I said you can use for raising any technical issues you're experiencing with the stream. For example, if you can't hear me right now, or the video is choppy or something, all right? You can use the chat section. Now, if you have any questions pertaining or regarding what the presenters are talking about, IPv6 related, you use the Q&A section of the Zoom client, okay? Don't use the chat section. It gets lost there quickly. It's easier to manage it in the Q&A section, all right? So the co-hosts can, they can look through it and monitor that easily when it's in the Q&A section. And of course, if you want to talk, if you don't want to use the Q&A, you want to ask a question pertaining to the presentation itself, you can raise your hand and one of the moderators will allow you to speak when it's time, and then you can talk and ask the question, all right? So, ladies and gentlemen, welcome again to the first live session for the 6th edition of the 02 Certified IPv6 Engineer cohort, online cohort. So today, we're going to be covering 2 of the 3 topics that you're supposed to cover this week, all right? And basically, the main presenter today will be Bashir Angode, as you can see, to my my right here. I don't know what it is on your own screen. So Bashir Angode, but I'll also be chipping in here and there. All right, so we're going to be covering, let's see. So welcome to live session 1. Let me go to the agenda. So this week, or this session, sorry, because ideally this week you should have covered IPv6 foundations, basic IPv6 config, and create the perfect IPv6 address plan. But in this session today, we're going to look at IPv6 foundations, and then we're going to look at configure basic IPv6, and then we open the floor for questions, and then there will be a survey to just a quick survey, tell us how we did, and then finally we will look at the winners. And in this session, because remember on Monday I mentioned that we assign points. There's a leaderboard in the group. Well, because of the technical challenges, we kind of tweaked that a bit. So what we'll be doing now during live sessions, we are going to be taking part in interactive quizzes, and there's then going to be a leaderboard that you'll be seeing on your screen. So what we advise is that when you join the Menti, because it's a Menti also, we advise you to join with the name you used to register on this session. So don't use any nicknames, like Flaming Dragon or something. Just use your real name. And when you join the quiz, the interactive quiz sessions, and then, because at the end of the session today, we will see who will be at the top of the leaderboard. You will see how well you are doing as the session progresses. But at the end of the day, or the end of the session today, we will see by your name, your actual name, who is at the top of the leaderboard. And we're going to select the top 5 on the leaderboard for awarding the discount vouchers for this session. All right. So, ladies and gentlemen, welcome again. I will hand over to you, Bashir.
Okay, perfect. My screen is visible. So as Ola mentioned, once again, I'd like to welcome you to this session. And basically in this session, we'll be talking about IPv6 foundations and basic configuration. So the first 2 courses that you should have done. So we're going to look at them in depth. So I believe if you've already done the courses, well and good. If not, we're going to cover them in depth in this session. So we look at the implications of IPv6 exhaustion, and then address basics, and then basic configuration. So for the rest, we'll keep on, because I know the agenda is long here, so don't be worried. We'll be going to cover all these things, right? So today we just focused on IPv6 foundations and basic configuration. Then with the next weeks, we'll be looking at the other courses. So we'll start by the mentees that Ola mentioned, right? So you can see my screen. I'd like you to head over to menti.com, or you can even scan the code, the QR code. And as Ola mentioned, please use your name because you're going to use the leaderboard at the end to award free vouchers, right? So menti.com, I see 2 players, 3 players ready. Ensure you use your name, right? 11, how many of us are here? 100 and something, right?
Yes, we have 122.
Okay, that's good. So let's get to at least 50. 36. 42. 47. So don't miss out on the fun. It's going to be fun. 52. And something else to mention, the quizzes are timed, right? So some of them are 20 seconds. So the faster you answer it, the higher the number of points you get, right?
Correct.
Yeah. Okay, so we can start. So the first question is, which of these options has extended the lifeline of the IPv4 address space? Is it BGP? Is it NAT? Is it IPv6? Is it DHCP? So 10 seconds, 7 seconds. I see 48 of us, 49. Some are still thinking. Okay, so most of us got it right. It's NAT, right? Network address translation. So we are here because we want to learn about IPv6, right? And IPv6 is developed to solve shortcomings that IPv4 had, right? And these shortcomings were even identified as far back as in the late 80s. If you look at some mailing lists in the 1980s, I've seen one from 1988 where people are raising concerns about shortages of, or not shortages, or about the addresses being depleted, because that's the time where the internet started growing, right? So NAT is just one of the measures, right? You know, RFC 1918. So you have private IPs internally, public IPs externally. Before NAT, all devices used to get public IPs. And right now, because of the shortages, most networks will implement RFC 1918 internally and then do address sharing for communication to the internet. So the answer is NAT. Let's see who's first in our leaderboard. Yeah, so we have Jeremy. I was first. We have Robert and Emmanuel. So you can see your position. So this is the guy to beat, right? Jeremy. So let's proceed. The first thing that we'll look at is the exhaustion, which I've mentioned as we were talking about the mentees, right? About NAT. And it's not just only NAT, we have CIDR, VLSM, we have various measures that were implemented to at least extend the lifeline of the IPv4 address space. So let's look at exhaustion. So this is the central IPv4 address pool as at, I've updated the dates as of today, as of 2024, today. This is a central IPv4 pool. Central IPv4 pool, we know the hierarchy of IPv4 or IP resource allocations, right? So we have IANA, and then IANA distributes these resources to the various regional internet registries. So is there something that you can note from this image here? I'll just check in the chat. Is there something that you can identify quickly? Looking at this image, what can you notice? On the right, we have the legend, right? used, free, and usable. Someone says almost exhausted. Not almost, but most of us, we got it right? There's no free IPv4. So of course, the central pool, we don't have IPv4 available from the central pool, but RIRs had some available space. Currently at Afrinic, we have close to 1 million IPs, right? Left, IPv4 addresses, and that's little, right? If you do the maths, you can do the maths of 1 million IPs left. It's not much, right? So you can see the problem here, right? So with this in mind, it's the reason why we are here talking about IPv6. Going back to history, you'll notice that the global IPv4 address distribution is and was unbalanced, right? So if you look at North America, so this is the number of IPv4 addresses per person in all the continents, right? North America has the highest because obviously the internet was developed in North America, right? So it makes sense that they had the largest pool of resources for historical reasons. Look at Africa, where we are. So Africa, we have 0.1 IPv4 addresses per person. And if you look at the growth of the internet, it just means that we cannot keep on relying on IPv4 to sustain the future development of the internet, because the internet is growing and resources are exhausted, right? So either people keep on doing NAT, you bundle a lot of your customers behind NAT and sharing IPs, or we move to IPv6. So these are some of the drivers as you are looking at IPv6. Yes, it's good to learn how to configure, typing in the command line, but looking at the history of where we came from, we can be able to understand the importance why IPv6 is important and migrating to IPv6. So currently, the cost of a single IPv4 address in, if I can call them the black markets, if you want to buy an IP address, single IP, it's $50 per IP, and it's rising. I remember back then when we're doing this in because we keep on updating the slide, right? We started from $20, if you remember all that, right?
Yes.
$20, $25, $35. So the cost per IP currently is $50. And this is not you coming to Afrinic, like getting an IP, because they'll get a point whereby when the 1 million resources, 1 million IPs I talked about available will be exhausted, right? So the only option for you will be to either deploy IPv6 or get these addresses from somewhere else. And the cost of these addresses is very, very high. And if you think about it, since this is a scarce resource, so it's going to obviously have a lot of people scrambling to get these resources, right? So with the increase of cost per address, right, it means that you either need to deploy more NAT, which, as we all know, NAT increases complexity. It breaks the end-to-end model of the internet, the initial end-to-end model. And with NAT, for those who run CG NAT, you know the cost of those boxes is quite high. And yeah, it cripples innovation. So remember, the early premise of the internet was open end-to-end. People could develop stuff in their own networks and innovate, but with NAT, it becomes difficult unless you implement some workarounds. So this is what I was talking about earlier on, the scramble for Africa, the real scramble for Africa. And we used to have this in our slides talking about it, but we are actually living it right now for those who are in the know, right? So since we are the only people who have IP resources left, it means that we are going to be deprived. With the address exhaustion, we're going to be deprived of the critical IPv4 resources needed even to move to IPv6. Because as much as we have IPv6 resources in plenty, we still need IPv4 because, you know, in the African continent, we're still trying to catch up in terms of deployment, right, and technology. So we still need these scarce IPv4 resources. And the two options that are left, either deploy greenfield IPv6 or IPv6 from scratch, or use more NAT, which is not sustainable. So for you, because I believe we're working with engineers or future engineers here in this session, there are several options. You can wait and see. You can deploy NAT on steroids, which again is going to be expensive, right? Or you can deploy IPv6. And I think that's the reason why you are here in this session, trying to learn or learning IPv6 so that you can build networks that are future-proof and also save costs on the way. So I think, I don't know if there are any comments or questions in the chat as I'm talking.
No, sorry about the mentee.
Okay, good. Perfect. So, but at least sometimes it's good to, as much as we're engineers typing, it's good to know like the implications of why we're doing all this. So if there are no questions,
Explain that on steroids.
yeah, explain. NAT on steroids is people implement, let's say if you have 10,000 users and let's say 5,000 users sharing an IP. So the NAT boxes have a limit, right? The more number of users that you add into your network, the more number of NAT devices that you need to do, or the more NAT you need to do in your network, basically. I hope it makes sense. Aura Kennedy. Perfect. NAT on steroids is the same as dual stack. No, that's different. We'll talk about dual stack in upcoming weeks. Dual stack is you running both IPv4 and IPv6 concurrently. Transition, again, let me repeat, if you have a question, put it in the Q&A. For the chat, it's just for any random chats that you may have, right? Or banter that you may have. If it's any specific question, put it in the Q&A and then look at it. Is there a plan to run IPv4 and IPv6 side by side for a transition period? This has been happening since 1994. Like I mentioned, the concerns about IPv4 exhaustion started even in the late 80s. IPv6 became an internet draft, was proposed in 1998, RFC 2460. So there's some people who've been doing IPv6 even since the 90s. So IPv6 isn't new. People have been running both IPv4 and IPv6 concurrently. So let's look at IPv4 addresses. And I'm going to hand over to Ola, but before I hand over to Ola, when you look at the TCP/IP model, right, we just want to make a comparison. We know the TCP/IP model, right? Application layer, transport layer, and in red, we have IPv4 at the network layer or layer 3. So if you look at IPv4, we have the layer 3 protocols, ICMP, IGMP, IPsec, NAT, OSPF, etc. Let's look at IPv6. You'll notice that nothing changed, right? At the application layer, we still have the same protocols. At the transport layer, we still have the same protocols, TCP and UDP. At the network layer, we have some slight changes, right? Instead of ICMP, we have ICMPv6. Instead of IGMP for multicast, we have MLD for multicast in IPv6. IPsec is the same, and neighbor discovery was introduced in IPv6. We'll talk about this next week. Ola. Then the various routing protocols also have support for IPv6. What's important here, the only change that happens is if you look at layer 2, at layer 2, you have what we call the ether type. So in IPv4, there's an ether type for IPv4. Can't remember it out of the top of my head. Someone will probably type in the chat. So that's the difference, right? When a device receives a packet, checks the ether type, and then the ether type specifies whether or identifies the upper layer protocol, whether it's IPv4 or IPv6. I think for IPv6 was 86DD, and then for IPv4 it's 0800, if I'm not wrong. Someone will probably confirm. That's the only change. At the other layers, everything remains the same, but what changes are just the specific protocols like ICMP, ICMPv6, and IGMP. So I'll hand over to Ola to talk about these IPv6 addresses.
Briefly. All right. So I just a quick story back maybe what 2007. Don't know if I'm giving away my age, and when I just started, you know, the introductory of network computing. I remember I was, you know, talking to a friend of mine. He worked with a big ISP back in Nigeria then, and I was like something on IPv6, and I was like, no, don't talk about that. It's too complicated. It's, you know, the way it's written and everything. And as you can see on your screen, when it's exploded to 128 bits, not even in 32 bits like IPv4, it looks a bit overwhelming. But of course, there are mechanisms in place to make this more simple, something to, you know, for easy to digest, and for us network engineers to be less, I mean, to be more recipient of it. So like I said, on the previous screen, you can see it's 128 bits in length. So that's 4 times that of IPv4. But then again, it comprises of 32 nibbles, right? So, you know, the main difference between IPv4 and IPv6 is that IPv6, because of that long, you know, the long next in bits, it's written in hexadecimal, which, you know, the value, you know, 16 values ranging from 0 to 9, and then A to F. All right. So, okay, sorry. So so you can see the number in the middle, the one with, you know, the colorful one, the colorful ones in the middle, because those are hexadecimal values of an IPv6 address. All right. And then, you know, each one is exploded to show them the decimal values. All right. So each decimal value is 4 bits. All right. So the one like the 2, for example, in the beginning, if you split it up into decimal or into binary, sorry, it's 0010. That's 4. That's the nibble I mentioned earlier. Okay. So 0 is all zeros in 400, and then 1 again is 0001, the one at the end, as you can see. All right. So each of those hexadecimal values in the IPv6 address comprises of 4 bits, and that's why it's called a nibble. All right. So there are 2 rules for shortening IPv6 addresses. All right. So normally well, let me jump ahead. So the first one is the zero suppression rule, where you strip off all leading zeros. Okay. That was the moment for me when I discovered that earlier, back to simplify IPv6 addresses when you write them out. And then the second one is to use a zero compression rule, where you replace groups of contiguous zeros with a colon. All right, that's how you compress.
And I know probably like you mentioned, the first time, if you're new to IPv6, right, you will see this address over here, 2001, blah, blah, blah. It just makes you think like, what am I doing here, right? It is something, a lot of maths here, something complicated. But I think, like you mentioned, even you, when you saw it first, right? After some time, you became used to it. So the more you do it, the more you become used to it. So don't let these numbers and letters intimidate
you. So yeah, so I mentioned the 2 rules, the zero compression and the zero suppression. So in the case where you have zero compression, as you can see on my left, I don't know what's for your own screen, the one in between the blue 2001, we've compressed. That means the groups of contiguous zeros, we've replaced them with colon. All right, and then on my right, where we've implemented a zero suppression, those zeros, the leading zeros in that group are removed. That's why you can see the orange one, it's not just 1 0. So 3 zeros have been removed. The magenta colored one there, you remove the 3 zeros also, and then the brown one, you've removed the 3 zeros. So that's the zero suppression. Now, normally your operating system will do this for you, actually. You wouldn't do it yourself. Your IPAM, I believe, does it for you also. So your IP address management system. So most of the tools you use when you're going to implement IPv6 will help you with this, but just, for you to be aware of this. All right. So these are the examples also of zero suppression and compression. Remember, suppression, you remove group of leading zeros, and then compression, contiguous zeros are compressed, and you just put a colon. And I believe you usually do the compression, maybe select structure of the IP address. So the IPv4 address, your interface ID, so 192.168.1.0/24, whatever, the host part of it is, I'm saying in IPv6, the host part of it is what you usually want to compress, all right? You don't want to touch the prefix, the network, the subnet part let me talk about IPv4, the prefix part of it. So where you see the 2001, blah, blah, if you say /64, for example, that means the first 64 bits, you're not going to compress that, all right? You leave the prefix part intact, or you can compress or do whatever you want with the interface ID. So yeah, so those are the two rules for shortening IPv6 addresses, which you don't have in IPv4, but it makes it much more simple. And I said there are tools. The tools you're going to use will do it for you automatically anyway. So don't be afraid when you type in a full address, and then when you do a show IP, whatever, you see something else like, what the hell happened? So the tools will do it for you. All right. So you have a scenario, in front of you here. You have this long address with contiguous zeros on both left and right, and you see the zero compression rule applied to both. Can someone in the chat explain why, tell us why this is wrong, or how this can create a problem? I see Christopher says you can only compress once. Yes, but why?
Why? Why? Best practice, is that the answer?
So I see something before. A lot of answers.
They're coming in, huh?
But I saw one before it went up. It will be difficult to bring back the actual values. Yes, but that's a bit ambiguous also.
Confused. Emmanuel says confused about how many groups on each side.
So that's a I think that's a more elaborate answer. So yeah, so if you compress both sides, how will you know which side has in the red and green one, which is what I don't know how many bits is that? 4 times 8, yeah, 16, and then the one that's 24 on the right side. Okay, so you can only do it once, and the way the operating system or whatever can calculate, because it knows it's not going to exceed 128 bits, and it will insert the appropriate number of zeros. So if you do it twice, it's going to be a bit tricky to know which one has 3 on this part, which one has 2 on the other part. Okay, so that's true. Right.
I think probably just to add, if you look at the address, right? Just to go back, I'll even use this one here. The IPv6 address, the groups, right? And that's how you know how many, you can even tell how many groups of zeros have been compressed, right? If you look at these here, you'll notice that there are 8 groups, right? Like Ola mentioned, if you count, there's the first one here, then the last one here, 8th one. So if you compress at the end, like in this scenario here, automatically you can count the groups here. You'll see we have group number 1, group number 2, group number 3, group number 4, then group number 5. So since the entire V6 address space has 8 groups, right? It just means you automatically, you can know that the number of groups here that have been compressed are 3 of them, right? Which are displayed here. So that's another way of looking at it and just understanding it in depth. But like Ola mentioned, you don't need to worry about it when you're doing your configurations. The systems handle this. So before we move on, we said the V6 address space is 128 bits, right? So with V4, right? With V4, the V4 address space is 2 to the power of 32, right? Which gives us around 4 point something billion. What about V6? What's the number? So I'll leave that as food for thought, right? 2 to the power of 128. I don't know if someone answered it there, but you can do this, do the maths and do the research. What's that number? 2 to the power of 32, that's 4 point something billion, what we know in IPv4.
Believe, as mentioned, it's I think
340. So someone said decillion.
Do you believe that?
Decillion.
I don't know. I see some Danny Isani says.
Kamal has even posted the the full thing, to the power of 128. So it's 340 and decillion. So we know in terms of money, I wish I could be an decillionaire one day in the future. So billion, trillion, zillions. Yeah, you can do that research. I think you can even nowadays with ChatGPT, you can ask ChatGPT about this, just to look at this massive size,
the scale of it.
Yeah, the scale of the IPv6 address space. Yeah, so Hafjul, you're an undecillionaire.
Danny is still saying, if you explain about the question, I think the compression thing is, if I'm correct, Danny.
Clear this. The ambiguous. This one here. Okay.
You're asking, explain again about the question. It says, let's see.
But I can just recap quickly, probably, if it's about the compression, right?
Okay. Yeah. So I think I said that Danny is on about which side to compress. I said, so it's better to compress the interface ID, not the network prefix part. Yeah. And then I think Danny wants to know why you can compress twice.
Okay.
Yeah.
You can't compress twice because of the ambiguity, right? It's ambiguous if you compress twice. Remember, we said there are 8 groups, right? With this entire, if you count the groups, you have 1, 2, and the last one is 8, right? So if you compress 2 positions, you'll not know how many groups are compressed here and how many groups are compressed there, right? If it's only once, you just need to count the current groups in that address, and you'll know how many groups have been compressed, right? I hope it makes sense. Yeah. So we have another question for you, Menti. So menti.com. If you're in the same screen, you'll just follow me, right? I'll also confirm on my phone if we're there. Let me start it. Okay, I can see people there. $60 players, 60-something players. Okay, I'm going to start it.
They're asking for the code, I think.
Yeah, the code, if you're not there before, right, you can scan this code quickly to join, in case you hadn't joined. But menti.com, the code is 73699474, or you can just scan the QR code there. So there's the question, which of this is the most compressed form of this IPv6 address? You have less than 20 seconds to select an answer. Ten seconds, you can see 48. Yep. So again, most of us got it right. So the most compressed form of this address is 2001. Remember, 0, we suppress it, right? So 2001 DB8, then we suppress 0 again, so CAB. Then we can compress the 4 groups of zeros, right? 1, 2, 3, 4. That would be colon, colon, and then suppress the last 2 zeros. So 1, 0. So here you need to be careful, right? I see the guys who chose the last option and the second last option, even the first option. You cannot compress the trailing zeros. Remember we said you cannot suppress the trailing zeros, right? You can only suppress the leading, the zeros at the front. So be careful with this, especially if you'll be doing the exam. These are some trick questions, right? Yeah, so be careful with this. But like we mentioned, you don't need to worry about suppression or compression in real life. So we have another one. You can just change. I'll also confirm we are all okay. Yes, the leaderboard. Last time was, I forgot the name that was at the top.
Jeremy or something. Jeremy.
Okay, Jeremy. So let's see who's if he's still at the top. Okay, so most of us got it at this nearly the same time. Huh? So still the person to beat is Jeremy. But remember, like we said, top 5, right?
Top 5.
At the end of this. Yeah, top 5. So we have another one. Menti.com. You can just follow me. You'll be...
Before you start. I've started. Okay, no worries.
Yeah.
So I see someone saying it's being rushed. You need to, it's time-based. You need to, can see, the faster you answer, the faster you be at the top of the leaderboard. So I need to explain that before I start.
Okay, so this time around, I think we have more players, right, joining, which is good. And again, like I said, it's all about, as much as we're doing these fun activities, winner, it's all about learning, right? If you have any question about the quizzes, if it wasn't clear, please put it in the Q&A so that by the end of this, we also clarify. So we have 105.
QR code.
Okay, let me share. The QR code is displayed. So I think I don't see any new, 111. Okay, so I can start. So it's similar to the previous one about compression and suppression. So which of these is the most compressed form of this IPv6 address? This one should be easy. So 25 seconds. So expect everyone to get this right. What do you think?
Charles, I don't know. You say you couldn't join the quiz. I'm not sure. Can I use this QR code on the screen?
Yeah, just use the QR code. You're still not late, right? Just use the QR code and you can join us the point where we'll be. Okay, so if I had Ken, right? You remember the Ken? But it's all good. The people who say the colon, 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 1. Remember, even when you go back to the compression, right? You can only compress 2 times or a certain number of times. If you compress a lot of times, it becomes ambiguous, right? But I hope it will be clear at the end. But most of us, we got it right. It's colon, colon, 1, right? So remember, you're compressing all the first 7 groups, right? The first 7 groups, we compress them into colon, colon, okay? Then the last group, we suppress the first 3 zeros. So eventually, the address is, the compressed form of this address is colon, colon, 1. And the first group, you did the suppression, right? 0, 0, 0,
Yes.
0. So it's not that you are wrong, but based on the question, we asked which of this is the most compressed form of this address, okay? So the only wrong answer here, I could say, is the second last one, the colon, 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 1. The others are right. It's just that they are not the most compressed. So be careful with this, especially if you do the exam.
Someone is asking, why is the second to the last wrong?
The second to the last.
The one with 11 respondents.
Yeah, because you can't, it means something else, right? If you have colon, there's nothing inside the group. It's blank, right? It's like you're removing everything, which you can't do. That's why I said the first one and the second one, they're right because you have the zeros, right? You are suppressing the first 3 zeros. You have a 0, you have a colon, you have a 0, you have a colon. But with the last one, you have a colon, nothing, colon, nothing, colon, nothing. So it's not clear with the second last one. With the last one, we are compressing everything. There's a defined set of groups that we are compressing, right? 7 of them to be exact. So that's why the second last one is not correct.
Yeah.
So I hope that's okay. Let's look at the leaderboard. Is Jeremy still ahead? This one was easy. I believe everyone should have answered it at the same time. Yeah, so we have Jeremy still there at the lead, followed closely by
Robert,
Daniel, Wellington, Akim, and Jacqueline. So we hope the lady can be fast, right? To get challenge the guys. So yeah, that's it. Let's move to the next thing. Any questions so far?
So I see hands raised. I don't know if they want to talk. Michael Soroyeun, I'm sorry if I pronounced that wrong. And Olumide Olatunji and Abdul. So let me see the Q&A.
Hello.
Yes.
Yes, Michael.
Okay, yes, my question has been handled. Thank you.
Okay.
Awesome.
So if your question has been handled, also remember to drop your hand, right?
Yeah, I forgot to mention that house rule, please. So we don't think you still want to ask a question.
Olumide. Give him the chance to speak.
Olumide Olatunji. Yeah, it's muted.
Okay.
You can talk.
Okay, Q&A, maybe as we wait for him. Any interesting?
There's an anonymous attendee who, anyway, that's a question.
For the other,
yeah.
Okay. I think we've covered these, right?
Hello.
Labi.
Yes.
Oh.
Ensure you are the only one, or if you are together, one of you mutes, otherwise there'll be the feedback loop.
Yes, if you're in the same office listening to this, you might want to be only one person on mute.
Hello. Yes. Good morning. Yes, I want to okay, so I just want to find out, will the questions be shared with us?
The questions? No, the questions will be shared, but the slides, I mean the recording of this session will be shared.
Okay.
All right.
Hello.
This is this is Kimi, if I'm correct.
Kimi, yes.
Kimi,
correct. Yes, Kimi. So thank you for the interactive session. Please, I just wanted to get a clarification. My understanding with using NAT is to translate private IP address with public IP address. So I want to ask, using NAT, is there a limit that a single public IP address that is NATed to the private IP address, like the private IP addresses, is there a limit? Is there a limit that you can NAT to a single public IP address?
I think this will depend with the vendors, the
Mhm.
vendor specific. If you're doing Cisco, Juniper, the box you're doing it on, right? So I don't think, unless you'll add on this also.
No, but I want to know why you're asking for NAT. We're not encouraging that practice in this session, actually. But yes, there's a limit. And that's why you have NAT upon NAT. They want us to, they want what carriers do. Okay. So, there's a limit based on the vendor or the card you're using.
That's all right. Thank you.
Yes.
So we can, let's proceed. And how many questions do you have?
That's no, that's all.
Okay. Okay. Okay, good. So next thing that we'll look at are the IPv6 address types. And we'll start by looking at the three main types of IPv6 categories, right? So first one is unicast. Of course, these address types are also linked to communication methods, right? So unicast is when you're sending from one node to another node, one-to-one communication, right? Multicast is when you're sending from one to many, but not all, right? I believe some of these concepts, we should know this, right? And finally, anycast is from one to the closest, right? And with anycast, closest means the closest just in terms of the underlying routing protocol. Key thing to note, there's no broadcast in IPv6. So remember this. And multicast is critical to how IPv6 works. And we'll look at this in a short while. So let's start with the scopes of these addresses before we look at the actual addresses, right? So the scope of the address is basically the extent of uniqueness. So the scope can be link local, it can be global. So it's just the extent of uniqueness. When you talk of the global scope, it means that this address is public, right? Can be reachable over the internet, via the internet. When you talk of the link local scope, the scope of this address is only within a specific link. Okay, so remember these two items here, the scope, the extent of uniqueness. So with the global unicast address, currently we're using 200:/3 as the current global IPv6 address space. So any global IPv6 address that you see will start with 200, then a /3. So it means that it can get up to 3FFF. But basically, a global unicast address, the extent of uniqueness is it's reachable over the internet. In other words, you can call it public. All right. So with the global unicast address, I'll run over the sections. You'll have your global routing prefix. So it starts with the IANA. IANA allocates a certain block. I think it's a /12. We have 3 of them, I think, /12 or /16, if I'm not wrong. But we have the list of IPv6 blocks that have been distributed to the various regional internet registries. That's the first level. If you're in Africa, you'll come to us and we'll give you a /32, for example, or a /48, based on the type of, on the member type that you are. And it can even be more based on your requirements or your needs, okay? So that's the global routing prefix. And then you have a certain number of bits that are reserved for you to do your subnetting. So key to note here, and I know probably we'll talk about this next week also in provisioning. In IPv6, the last 64 bits are reserved for the interface identifier, okay? So it means that if you come to Afrinic, we give you a /32, you have 64 minus 32 bits that you can use to subnet your prefix. And even just doing the maths, 2 to the power of 32 means that you can get in 1/32 that we are giving you, you can get the equivalent of the current IPv4 address space, just 1/32. If you are to map this out to individual IPs, so you can picture the scale of the IPv6 address space. So at the bottom, you have an example of an IPv6 address. So in orange, we have the global routing prefix. In blue, we have the bits that were used, or the section that was used for subnetting. And we'll talk about this next week. Maybe 10 means something, 249 means something. You can do this in IPv6, creating hierarchical address plans. And then the last 64 bits over here, these identify the interface or are reserved for the interface ID. So that's the global unicast address. The next type of address, the linked local address. So with the linked local address, it's always generated once you enable IPv6 on an interface, a linked local address is configured automatically. And I just realized I've given you an answer to an upcoming question, which I hope no one will get wrong, right? So, but basically the linked local address is created automatically on the interface. It's always present. And linked local addresses are identified by, start with FE80, right? So if you do the maths again, the binary maths, the groups of 4, that's 1, 1, 1, 1. This is F, then 1, 1, 1, 0. This is E, and then this one here is 8, and then 0. And the next 64 bits are reserved and are always 0, right? And the last 64 bits, as usual, are reserved for the interface ID. So key thing here is the linked local address automatically configured and how to identify it, FE80. So we have a question which I leaked it, unfortunately, but to be to your advantage. So menti.com, I can see we're already there since most of us just follow along.
And for those who have been having difficulty to join, you can scan the QR code now. There's no URL.
Scan the QR code and join the fun. So I see 105, 6, 8. So this one should be very fast, and I gave you the leakage. Okay, so I'll start it up. So you can configure the same link local address on different interfaces on the same node. True or false? So this was a tricky one, right? Because most of us, we got it wrong. 58 said false, and 38 said true, which is right. So the answer is true because remember the scope of the link local address is only within that link, right? So if you have one router, the same router, and you configure the same link local address on different interfaces, it's going to work, right? If you do FE80::1 on, let's say, gigabit Ethernet 0/1 and FE80::1 on gigabit Ethernet 0/2, it's going to work, right? Because those two interfaces are in two separate links, okay? So it's something worth noting in IPv6. You can do the same link local address on different interfaces. And in a short while, we'll look at measures that, because I know probably we said false because duplicate, we were thinking about duplicate address detection or the addresses being duplicate, right? But there are measures which have been implemented to prevent this. and I'll mention this in a short while. So leaderboard, let's see if Jeremy is still at the top. Okay, Hakim is at the top now. So Jeremy, I hope you didn't disappear. Did you? Okay, I see him at 5th, I think. Yeah.
Maybe it was able to work.
Yeah. So we have another one here. Menti.com. You'll just be navigated to this quiz. Let me start it. $121. I think we're already there. I can start it up. You type ping FE80::1 on the router's terminal. Which interface does the router send out the packet? So there's an image here which you need to analyze. If you type ping FE80::1, which interface does the router send out the packet? Is it FE0/0, FE0/1, or none? So we have 8 seconds. And yes, most of us got it right. So it's none, because if you type ping FE80::1, remember what we talked about, the link local addresses, right? You can have the same link local address on even different interfaces on the same router, right? So in addition to you entering the link local addresses, you need to also specify the exit interface. Okay, because you can have the same, like you mentioned, that the same link local address in multiple interfaces. So on Cisco iOS, on most platforms, if it's on a router, you need to specify the exit interface that will be used to send out that packet. So let's look at the leaderboard. Okay, so Hakim is still at the top. And like I mentioned, for the rest, as long as we just because you're not at the top, yeah, don't feel sad or anything, right?
Yeah.
So at least I hope you're learning something from the discussion. And if it's not clear, Q&A and we'll answer. So we've talked about the link local address, and this was the quiz, right? Which I've just mentioned. In addition to you entering the link local address, let's say if you're testing reachability or pinging, you need to also specify the egress interface or the exit interface. So that's on the routers. We also have, we can resolve link local address ambiguity with what we call zone IDs on hosts, right? So it's basically the same thing, whereby at the end of the link local address, you have what we call a zone ID, right? So %, then a zone ID. So basically the zone ID will identify the address scope, right? So if you have a node or a host that has 2 interfaces, these 2 interfaces are in 2 different zones, right? So that in case you want to test reachability or send out packets using link local addresses, you're going to use the right zone to send out the packets, right? So on macOS, the zone ID is usually the interface name, for example, EN0, %, EN0. On Windows, it's usually a number. So if you do ipconfig and you have link local addresses, you'll see the link local address and then the zone ID, the %, and a number if it's on Windows, or the interface name on macOS. So it's the same concept we talked about on the routers, but this is now for the host. Always picture link local addresses on the interfaces being in different links, right? And how do you resolve ambiguity on these links using zone IDs and on the routers specifying the egress interface. So we have another question. I think I skipped it. Yeah, we have another Menti. So I have the QR code. So we can see 118 players already. That's a good number. Let's start. So again, this one you need to check the image. And the question is, select the command you'll use to telnet from node A to node B. So there's an image there. Which command will you use to telnet from node A to node B? So it's all about the zone ID. 80 guys, 90 people, I'll fill it in. 2 seconds. So the answer is the second one. And I think probably I didn't mention that the zone IDs are locally significant, okay? So if you have the scenario I mentioned with the 2 interfaces on one host, right? So the zone ID that will be configured is locally significant. So that's why I hope I can show you. Let's look at the leaderboard first quickly. So, okay, Robert is now the lead. So I hope I have that question. No, I don't have it. The image. But basically, the answer to the question was the second one, because you used the zone ID of the interface, not the node B. It was from node A to node B, right? So you don't use the zone ID of that node that you're trying to reach, right? Because that zone ID is locally significant. So for it to be right, the right option will have been ping the address of what you're pinging, and the next quiz is the same thing. So telnet, the link local address, and then your zone ID, the zone ID for that interface that's connected to the node you're pinging. So don't pick the entire address plus its zone ID, because the zone ID is locally significant, right? So in other words, if you're on host A and you want to reach host B, you need to use host B's link local address, but use your own zone ID at the end, okay? Because host A doesn't know about the zone ID of host B since it's locally significant. So let's see whether the next one will be better. I'm going to start it up. I'll show the QR code. So it's in the same line. It's in the same line. So I think I can start it. 120 of us. Confirm. So this time around, it's from node A to node C. Select the command you'll use to ping from node A to node C. Eight seconds. Yeah, so this time around, most of us got it right. So node C, its link local address was FE80::C. And then you need to use the zone ID on node A, okay? Not the zone ID on node C. For you to get reachability to ping node C. So I hope any question regarding that, maybe you can also help me check as we look at the leaderboard, if there's been a change.
No, other than the only question regarding link local addresses was asking if they are private addresses. Link local addresses, private addresses.
So we can't call them private because in a short while, I'll show you in IPv6, we have the equivalent of the RFC 1918 private addresses, the ULAs. We'll look at this in a short while. So link local addresses, we can't call them private, but the scope is not, since the scope is not global, they're only reachable on the specific link.
And we will see the use of them actually, because I just been thinking what the hell is that? I mean, just link local, yeah, so what? Well, you're going to see next Friday when we look at mastering NDP, you will see the use of link local addresses in IPv6.
Okay, it's actually the next thing. The unique local addresses. So with the IPv4 RFC 1918 private addresses, in IPv6 you have the unique local addresses. But like we mentioned, the address space is so large that the use cases for this are very minimal, right? Most of us will never need to configure ULS internally, right? So for the ULS will be identified by the way you identify ULS, they start with FC00/7, but currently we're using the FD. Any address that starts with FD00:8, that's a unique local address, or that's a private address if you're trying to equate it with what we have in IPv4. But like I said, for most of the time, you'll be doing global addresses. Remember, I know most of us are usually tempted coming from the IPv4 world. Most of us ask us the equivalent of private IPs because we always believe that with NAT, you have a more secure network, right? But that's not the case, right? The NAT was not initially intended for security purposes. It does the security by hiding, but security by hiding is not actual security. So in as much as you're using global addresses everywhere, it's now important in IPv6 to do your firewall rules properly and to ensure that security is handled by proper security configuration has been done. So of course, like I said, you can do private IPv6, but for most of us, it's not something that you'll be doing. You'll always be using your global IPv6 address space, since the address space is also large enough. So we've talked about the first portion, the network prefix, where we talked about the link local address, the global unicast address, and the unique local address, right? The last 64 bits, there are several ways these 64 bits can be generated. The first method is manual or static. So this is recommended as usual for servers, routers, right? So you can do something like your prefix, : something. Prefix, : 10, A, B, whatever. Then the other automatic methods of configuring the last 64 bits. The first one is EUI64, which I'll mention in a short while. It can also be done cryptographically. So this is with the secure NDP. And the last one, it can be pseudo-random. So just a random number, random numbers, as long as they fit into the 64-bit boundary. So let's look at the IDs that you can't configure or that are reserved. It's not recommended that you do the all zeros, right? You can do this on some platforms, but we advise you not to do it, even if the platform allows you to do it, right? Because the all zeros is reserved for the subnet router Anycast. So if for one reason or another, you have multiple routers in the same subnet and you want to do Anycast on those routers, use this last 64 bits you configure all of them with this last 64 bits, 0000000. And the next one is subnet anycast, the next range, right? We'll share the slides and you can see the exact ranges, but the second range over here, so this is used for subnet anycast. If for one reason or the other you want to do anycast inside the subnet, right? You can use the interface ID from these ranges over here to configure your anycast devices in a subnet if you need to do that. So this is the last 64 bits or the last, the interface identifiers that are used for the subnet router anycast and the subnet anycast. So with EUI64, you're going to use the MAC address of that interface, and a MAC address is usually 48 bits, right?
Right.
So start from 48 bits. Remember, the target is to have 64 bits, right? Start with 48 bits MAC address, then modify it by adding FFFE. So FFFE in red, right? So FFFE, how many bits are those? 16, right?
Mhm.
So 16 plus 48, you have your 64-bit identifier. And then usually you'll flip the 7th bit, right? In the first group over there, right? Will be flipped from 0 to 1 or 1 to 0 for unique or non-unique MAC addresses. So the resulting MAC address will be 0, the resulting interface ID, not MAC address. The resulting interface ID will be 0290 blah, 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 then 0F. Something to mention, there's a problem with this using the MAC address as an interface ID. And this was identified some time back. Picture this, you are the office and your address is generated using your MAC address. You go home and your address is generated using your MAC address. You go to maybe you connect to another network somewhere else and your address is generated using your MAC address. I hope you can see the problem, right? So the problem here is what we call the privacy concerns, right? Someone can be able to track your activities just by looking at your MAC address, right? Since the first bit, the first 64 bits will depend on the network you're on, but the last 64 bits will always be the same, right? So your activity can always be correlated based on the network that you're on. So that's why nowadays EUI64 is not used. And even new in your networks don't use EUI64. By default, Linux and the other Windows, I don't think they use EUI64 apart from link local addresses. But for the global addresses, you'll notice that either it's a random number that's been, most of the time, it's usually a random number that's been generated due to the privacy concerns of EUI64. Some other well-known addresses, we have the colon. Colon is all zeros, right? So this is the unspecified address. I think you'll do next week, right?
Yes.
Unspecified NDP. So unspecified just means that the host doesn't have an IPv6 address
yet.
Maybe it's trying to get an address and it will use this colon as the source IP. And yeah, it's never used as the destination and the scope is only within the link. So routers cannot forward packets with the source of colon past the link. And colon/0, we know this from IPv4, right? When you do 000/0, the entire IPv4 range, and in this case, this is the entire IPv6 range. :1, we looked at this in our quiz, right? So this is the loopback address. In IPv4, this is 127.0.0.1, right? And this is the equivalent in IPv6. So for anycast, we mentioned anycast. Anycast should be communication to the nearest, right? So let's say if you have several servers in Kenya, Mauritius, South Africa, and I'm near South Africa, you want me to be directed to the server that's near me, right? So that's the purpose of Anycast. And nearness is determined by the routing, the underlying routing protocol and topology. And basically with Anycast, use the same address, unicast address, use the same unicast address on multiple nodes or interfaces. So before we jump to multicast, anything of concern which you can address quickly? We're good, right?
No, yeah, we're good, sorry.
Yes. // /0, yeah, Mohammed, yeah, default like IPv4. Then 000/0.
So please, if you want to post the questions, like I said, in the Q&A section, it's easier to manage there than in the chat section.
Okay, so we can look at multicast. So multicast, remember initially when we were looking at the types of communication, we talked of unicast, then we've talked of anycast, and we said there's no broadcast in IPv6, right? So with multicast communication, you are sending traffic from one to many recipients, right? One source, many recipients, but not all. So to identify a multicast address in IPv6, you'll identify it. It always starts with FF, right? Anytime you see an address that has FF, just know this is a multicast address. Then the next portion of this address, I'm going to summarize this just to mention the key parts, right? So the next important thing is the flags. The flags can either determine whether the address is dynamic or non-dynamic. And the scope, I'll show you in a short while. It will be easy to understand all these sections. Then most importantly is the group ID. So in multicast, you're going to join a group, right? And then based on the group you've joined, you're going to be receiving traffic that is sent only to that group. Remember, the main purpose of multicast is to avoid sending traffic to everyone. So everyone on the link, for example, should not be receiving unnecessary traffic. So you join a group and then you'll be receiving traffic sent to that group. So let me show you an example. Yeah, with the scopes, I'll start with the scope before we get to the full address, right? So FF 0 something, FF something something. So the first thing we look at is the scope. The scope is what we've been also talking about with the address scopes, right? And with the address scopes, we started from global, link local. Same thing applies with multicast. So you can have an interface local scope, meaning that the extent of uniqueness of this multicast address cannot span past the interface. Okay, so I hope you can picture this. So the best way to understand this is, let's say if you have virtual machines, right? Virtual machines will be inside one server, for example. So the extent of uniqueness, if you configure an interface local scope, it means that multicast traffic will not get out past that interface. That's interface local scope. It's the smallest scope. If you expand it slightly, you have the link local scope. So the multicast scope is, the extent of uniqueness is within a link, right? So if you have, if you're connected to a certain subnet, you can be able to receive multicast traffic inside that link. Then of course you have admin local, site local. These are custom, right? Based on your network. But for our case, most of the time we'll be dealing with link local scope at this level that we are at, right? Then finally we have the global scope, which is the E. So I'm going to show you the scopes, how they relate to the address itself, right? You can easily identify the scope from the multicast address. So here's an example of a group ID with different scopes. So the group ID is the same, right? 101, and 101 is the group ID for NTP servers. So if you have multiple NTP servers and you want them to be reachable via multicast, to join this group, this is what will be. They'll be reachable via these multicast addresses here. So first one, the scope is this column over here that I'm highlighting, right? FF01. So this interface local scope, all NTP servers on the same interface as the sender. FF02, and this is popular. We'll be looking at FF02 next week, because most of the time you'll be doing multicast on the link, and the multicast operations for neighbor discovery will always be happening on the link, right? So FF02 is what we'll be looking at frequently, yeah, and next week. So FF02::101, that's all NTP servers on the same link. I hope you get the picture now. All NTP servers on the same site as the sender, same organization, all NTP servers on the internet. So if you ping on the link, if there's an NTP server, it will have joined this group here, 101, right? So if you ping FF02::101, all NTP servers are going to respond. So here, most importantly, are the well-known multicast addresses, right? So FF01::1, one always means all nodes, right? All IPv6 nodes. So FF01 is all IPv6 nodes on the local interface. Again, for us, we'll be mostly dealing with FF02::1, which is all nodes on the link, right? On the local link. So if me and Ola here, if I ping FF02::1, we're going to get responses from all the IPv6 nodes on this link that we are on. Then next one is FF01::2, or most importantly, 2 as a group ID, right? So 1, as usual, is the all routers on the local interface. So 2 is routers, right? And FF02::2, all IPv6 routers on the local link. So if you've configured V6 on your network and you ping FF02::2, all the routers are going to respond. So the RFC down here has the complete list. But for us, like I mentioned, you just need to remember FF02::1, all nodes on the local link, and FF02::2, all routers on the local link. So the next thing, so we've started from multicast, right? We said that if I've configured IPv6 on my device, the interface is going to join. First of all, if it's a host, it's going to join FF02::1. Okay, and then it will be waiting or listening for interesting traffic on this multicast group. Okay, if it's a router, the interface is going to join FF02::1 and also FF02::2. This if it's a router on the link, right? So remember this. So you have the various groups. The next type of multicast address is what we call the solicited node multicast address. So with the solicited node multicast address, I'm going to explain it with the, and Ola will also look at it next week, right? Yeah, in depth. But basically, I'll just explain it from the concept of ARP, right? So let's say if I have host 1 here, and I have host 2. So all these are connected to a switch. Okay, so with ARP, I believe we know ARP, right? The Address Resolution Protocol. So if I want to communicate to host 2 from host 1, maybe I want to ping host 2. So host 1, let's say the address is 192.168.10.100, and host 2, the address is 192.168.10. Let's say 200. So the first time that you're trying to send packets from host 1 to host 2, you'll need, of course, you have the source IP, you have the source IP, which is that, the destination IP, which is host 2's destination IP or host 2's IP, right? And then in addition to that, you also need the source MAC address and the destination MAC, right? So in IPv6, just to summarize, in IPv4, you'll do with ARP. ARP will send a broadcast message to everyone, okay? So everyone on the link is going to receive a message. Can the person who has this IP, the .200, send me your MAC address, okay? So since IPv6 we don't have broadcast in IPv6, what's going to be done is we're going to use multicast. So let me explain how that happens. There's that. So the same scenario, host 1, we want to know the MAC address of host 2. So what do we do with multicast? So the first thing that will happen is any address that is configured on these hosts is going to have an equivalent solicited node multicast address. It's going to join an equivalent solicited node multicast address group, okay? So first of all, we said the host is going to join FF02::1 since it's a node, right? And then if I've configured this address on the host 2001 DB8::1, and on host 2, 2001 DB8::2. So for each of these addresses, in addition to this multicast group, the host is also going to join the solicited node multicast group, okay? So it's going to join SNMA group for both of them, right? SNMA. So here the point is, just by having my address, I can know the multicast address that that host has already joined, right? So host 1 over here already knows the solicited node multicast address of host 2 because the solicited node multicast address is derived from the last 24 bits, okay? So what is going to happen here is the host, instead of sending a broadcast message, it's going to send packets to the solicited node multicast address, which it already knows based on the last 24 bits here. So it becomes much more efficient, whereby not everyone on the link is going to receive this packet, okay? And most importantly also, the switch needs to have what we call the MLD configured, multicast listener discovery. Because when this host is joining the solicited node multicast address group, it's going to send a report to the switch, and then the switch will know that host 1 is reachable over this interface over here. The interface on host 1 here is reachable via this interface on the switch. Same thing. I heard about a certain multicast address from this port, and I have a database on it, so that when someone is sending packets from host 1 to host 2, other ports will not receive that traffic since the switch already knows these multicast addresses or groups. So the address itself, it's computed for all unicast addresses, right? FF02::1:F. So this is the solicited node multicast. The first part of the address, which is 104 bits, and then we pick the last 24 bits of the unicast address, right? last 24 bits and have our solicited node multicast address. So with the example I gave you, 2001 DB8 : 1, the equivalent solicited node multicast address will be FF02 : 1 : FF, and then colon 1. So this is the equivalent solicited node multicast address. If you had another address that was : 2, to be the same thing, FF02 : 1 : F:2. So because by default, when I configure this address on the interface, the : 1 on host 1, it is going to join this group by default, right? It's going to configure this address by default since it's joined the group, right? And it means that host 2, if host 2 wants to reach this 2001 DB8 : 1, it already knows the solicited node multicast address or the multicast address that host 1 is listening on. So that's the brief introduction to this. Next week, you're going to look at this in details.
Yes, so I agree. So because I mean, all look very a bit fuzzy right now, but I believe, and I mean, strongly believe that when you see the application of linked local addresses, so solicited node multicast addresses, all this the multicast node addresses for IPv6 FF02, I mean 01 : 1 or : 2, all routers, all nodes, which he has mentioned now. This is the foundation. But when you see the application next week and how they're used, I believe you have a better, a deeper understanding of how these things integrate with IPv6. So don't worry about it right now.
Yeah. So if there's any takeaway from here is that each address you configure, remember in IPv6, you can configure multiple addresses, right? So each address you configured is going to also have a corresponding solicited node multicast address, or it's going to join that group based on its address. So here's an example. You just pick the last 24 bits, come up with the solicited node multicast address. So here's an example on an interface. This is on Cisco. So you see that we have, it also applies to link local addresses, right? In yellow, you can see that we have FE80, blah, 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 and then the last 24 bits. So that's the solicited node multicast at the bottom here. That interface also joined. So if someone tries to ping or is trying to ping and doesn't have the MAC address, since this interface has joined this solicited node multicast group, the traffic will only be sent to this interface and no other interfaces. Same thing with the global unicast address here. We also have a corresponding solicited node multicast address. Also note what we discussed, right? So we have FF02 : 1. So since it's a router is also a node, the interface also joins the all nodes multicast group, and then it also joins the all routers multicast group. So and then finally for this section, remember if you have your solicited node multicast address, right? At layer 2, you also need a destination MAC address. If you picture what we're discussing, and all I think we'll show them next week, right? So if you're pinging, you have a source IP, destination IP, right? And then the destination IP will be the solicited node multicast group. At layer 2, you're going to have your own source IP, but what about the destination? You're going to have your own source MAC, not IP, but what about the destination MAC? So this is where the multicast MAC addresses come in, right? So multicast MAC addresses start with 3333, and then you pick the last 32 bits from the solicited node multicast address, okay? So the last 32 bits from the multicast address, it's not only solicited node multicast, but the last 32 bits of the multicast address come up with a multicast MAC address. So just think of this at layer 2. What address do I use to communicate as I'm communicating with the multicast address? And examples here, so if it's all nodes, the multicast address is going to be this over here. If it's all routers, this is the multicast MAC address. And for this solicited node multicast address, that's the multicast MAC address. So that's it. I don't know if you have any questions.
Okay, well, I was just responding to what they said. Please differentiate between an anycast and unicast address.
So anycast, we said anycast is same IP, let's say 2001 BB8::1. Same IP can be configured on multiple interfaces or multiple nodes. You do the same thing. Okay, and it will not, if you specify the address as anycast, it's not going to, if it's on the same link anyways, it's not going to bring up the duplicate address issue, right? Then the other one is unicast. The other one is unicast.
Yes, what's the difference between unicast and anycast?
So let me even start from scratch, right? Unicast is an address that's configured on one interface, right? It's unique and can be used to send traffic to that interface, for example, that one. Anycast is also a unicast address, but because it can be configured on multiple nodes or interfaces, so that's why it's designated as anycast to avoid it being marked as duplicate. But anycast is also unicast, okay?
Yeah, so I think I gave the example of the 8.8.8.8 Google's public DNS server. It's an anycast address. It's definitely not one server in the whole world. It is the same address all over, and you get routed to the closest one to you. All right, so let me see. Why don't we have broadcast IPv6 address? I think I answered that, but
okay.
Yeah, there's no broadcast in IPv6. Yeah, a bit more noisy multicast, but there's no broadcast.
Yeah, because when you look at the history, it was IPv6 was a chance to redesign the protocols, right? Because even look with the example, if you look at the example I gave you with ARP, right? If I want to get your MAC address, even just next to me here, right?
Yeah.
If I somehow ping you and I don't have your MAC, everyone on the link is going to receive that message, check, and okay, it's not intended for me. So that should be in the case, right? So broadcast was removed to reduce noise on the link, right? Yeah. Is that it?
That's it for this section. So okay. Okay, something about textbook for IPv6. I will talk about that at the end of the session. I'll just mention it to you. So for God Listen Sumari, I hope I pronounced that correctly. I said when solicited node multicast address use. Like I said, next week, because I know it may be a bit fuzzy right now because you have so many things at the same time moving past right now. So, but it does have its use. We don't want to go beyond the scope of this live sessions, for me to explain exactly what it is, but it has a place, all right? And it's part of it is to reduce that noise Patrick just said now. So we'll look at that next week in neighbor discovery protocol.
So let's move on to the next section, which is IPv6 from an IPv4 perspective.
Yep. Yes. So to have a better understanding of IPv6, we need to employ some of our understanding of IPv4 because there are some similarities to, and then kind of apply to what we see in IPv6 now, what we're trying to look at in IPv6, so we get a better understanding. So, of course, when we say IPv6, usually the thing that comes to mind is that somebody he had a bank balance of 340 on the Cillian today, if I'm correct, and that's what comes to mind. It's a huge address space. But the thing is, there's more to the protocol than that huge address space, okay? And that's why, I can keep saying next week, we're going to see some of those numerous, the way the numerous what's it called, multicast addresses that I actually just discussed are going to be used. So to get a better understanding, we're going to look at the packet structure. So if you look at the header structure for IPv6, yes, it has the different fields. But if you see the red label in there with the squiggly there, there's the 40 bytes, and then the remaining it says variable length. Now, one of the things, the main difference, or one of the differences between IPv4 and IPv6 is this fixed header length. Now, in IPv4, the header length is variable, I think between 20 bytes and 60 bytes, right? But for IPv6, it is fixed at 40 bytes. So that means any device, for example, that is IPv6 compliant, knows that header is going to be fixed, it's going to process it faster, smoothly, it goes through quickly. Compared to IPv4, that it could vary between 20 and 60, you need to check the IHL field or whatever, and process something, and before it moves forward. So, but of course, the reason why the IPv4 header varies is because there are different options that can be added or removed at any particular time. So, but the way this is solved with IPv6, you have that section after the base header, the 40 bytes, the fixed one, which could be variable length. And that's where you have the introduction of extension headers. Okay. All right, so extension headers, as you can see, is similar to the IPv4 protocol field. In the IPv4 header, the protocol field points, the header is in layer 3, the internet or IP layer, if I'm correct, TCP IP protocol stack. So the protocol field points to the protocol in layer 4, what's carrying, okay, in the transport layer. All right, so it's similar to that. So the extension headers in IPv6, those that you find after the fixed header 40 bytes, all right? So it's the protocol field. So also it encodes additional internet layer information, and it's between the base header, that is layer 3, and the upper layers, transport and on. All right? So you can see here, there's an IPv6 packet with no extension header. And as you can see, it has the version, traffic class, full label, all that good stuff. But in the next header field, which is the protocol equivalent in IPv4, if it's an IPv4 header, you will see protocol. But here it's next header. It's saying, okay, there's no upper layer URL, okay? So there's no extension header here. So upper layer could be what? TCP, UDP based, ICMP, v6, which you will see a lot next week, and routing protocols like OSPF. So, but here, what you see on your screen, you have an IPv6 packet, with extension headers. So you can see now that you see it's a bit fatter now, but it's outside the base header. The 40 bytes is still fixed, but the next header field, the one in blue, inside the fixed 40 byte header, you can see there, is pointing to extension header 1, the blue one below, which could be, I'm going to show you a table shortly, which could be any of the extension headers, the variable extension headers you have. But within the extension header itself, you also have a field for next header. So because you can chain extension headers together. So in this case, the blue extension header you see there has a next header field, which is red, pointing to the next extension header after it, which is red below it. And then within that red extension header, which is EH2, I have a next header field again, the brown one, but this time around, there is no extension header after that. It's just the upper layer protocol. And that's why you have the next header field is pointing to the upper layer protocol. We could be any of those you see in the brown section of this field. And then after that, you have the data. Okay. So like I said, there are multiple extension headers. You could read about that. Don't crack your brain about it, but you can see the first one there is the base IPv6 header, and then you have hop by hop. You can see the description there, examined by all hosts on the path. Maybe one of them we might mention briefly, like number 5, fragment, fragmentation parameters. We'll see. And then destination options. So this is just a summary. So, like I said, to get a better understanding of IPv6, Yes, like I've seen the Q&A, people have been asking what are the security implications, why is there no NAT, well, why there's no broadcast and everything. Yes, you are bringing your IPv4 knowledge to try to understand what this new protocol is all about. And so here we're going to see some of the changes from IPv4, but of course you need to know what IPv4 is to be able to understand these changes. So like the red one you see there, those are the feeds, the fields. I'm hungry, I'm sorry. Those are the fields that have been eliminated. Okay, so the IHL internet header length, that's why I said because the base header is fixed at 40 bytes. You don't need that field. It's always going to be 40 bytes. It's not going to vary between 20 and 60 bytes. So that has been eliminated. And there's no need for the header checksum because it's always 40 bytes. You don't want to always calculating checksum because it varies. Okay. So the fields that have been removed are in blue. All right. So if you look at identification, flags, fragment offset, options, and padding, these are all related to IPv4 packet fragmentation. In IPv4, as a packet moves through routers or nodes, from source to destination, based on the MTU of the link, the egress, exit link of the router. If it's too small or smaller than what the packet is, it's going to break it up. It's going to fragment it. All right. Between the source and destination, that happens. It can happen. But with IPv6, you only fragment at the source. All right. Fragmentation does not happen between the source and the destination. No. So, one of the things it does is what you call path MTU discovery. When the source wants to send packet to a destination, it's going to test the link first to see the smallest MTU on that link, and then it's going to send a packet that fits that MTU size. All right. There's no fragmentation between the source and destination, but only at the source. So identification, which is used for IPv4 packet fragmentation at the source, between the source and destination. All right. So the flags for saying, for whether it's, I think one is reserved, one is for I don't know, I can't remember the flags, and then the fragment offset that mentions, that tells the destination node where this fragment belongs in all the fragment FPCs I've gotten. All right. And then the options and padding also. So those that have been renamed are the ones in green. All right. So type of service now have traffic class, kind of the same for QoS. Total length for IPv4, I believe it's the header plus the payload. But in this case, in IPv6, it's now changed to payload length. All right. And then time to leave, hop limit. All right. And then protocol, that's what I've been talking about since with extension headers. All right. That has been changed. Protocol is what you have in IPv4. All right. But in IPv6, it's called the next header field that can point to the presence of an extension header if it exists, or the upper layer protocol, which could be ICMP-v6, TCP, UDP based. All right. And then, of course, the fields that have been maintained are the source and destination address. That has not been changed, all right? So we always have source and destination.
And the version.
Okay, yes, and the version, yes. So, so now you have version 6, all right? So it's all in gray there.
Yeah. So there was a question actually, and someone even answered right now, because here we have removed. The key thing is removed from the base header, not removed, because the question was, what's the difference between eliminated and removed?
Okay.
Because eliminated, the fields are not there anymore in IPv6. Then the ones in blue have just been removed from the base IPv6 header to extension headers.
Extension headers, correct.
Yeah. So I hope it's clear, Michael and Abdul Hakim. Robert provided the explanation also. Yeah.
Thank you, Robert. Yes, not my still. They are still available in the but thank you very much. So yeah, so some more comparisons between some familiar concepts and things in IPv4. So for example, dynamic host configuration protocol. In IPv6, you have DHCP v6, which is different, okay? And then you have another one called stateless address auto configuration, which is SLAC for the acronym, which we'll be looking at next Friday. And then the link layer address resolution, we mentioned, Bashir mentioned address resolution protocol ARP, and there's broadcast in IPv4. But in IPv6, we have multicast, and then we have ICMPv6, neighbor solicitation, and neighbor advertisement. All right. And then some, just quick summary again, some key functionality comparisons. DNS, you have a record, all right, 32-bit, and you have for IPv6, it's going to be quad A because it's 32 times 4 to make 128 bits, all right? But she mentioned also the protocol for multicast, IGMP, and the version 3, the highest for v4, and then the multicast listener discovery protocol, version 2 for IPv6. And then default gateway auto provisioning. Yes, we'll see more of it next week. Let me just mention it here right now. Also, so we get over it. The only place you can get default gateway information in IPv6 is from the default gateway. All right, the router itself. It doesn't come from a DHCP server. Anyway, that can be issued. So that's the main difference you can see here in IPv4. You see DHCP the opacity RIP for IPv4, but IPv6 is only through a router advertisement from an IPv6 router. All right, on the node. And then yes, there's some all the routing protocols except there's one I saw on FR the other day I've never heard of, but all of them have v6 equivalents. All right, so even I think EIGRP is open source now. Even EIGRP, RIP-NG, OSPF, and the one with address family, the ones that didn't, yes, all of them have basically IPv6 support. All right, BGP version 4, not BGP v4. So with address family, IPv6 address family support. The same thing with OSPF. They have one OSPF version 3 and OSPF, the one with address family support. I mean, it supports address family v6 and v4. And then I remember I said the MTU size for fragmenting. So the MTU size for v6 is 128 bytes. All right, and the supported communication modes, again, summary, no broadcast. All right, no broadcast in IPv6. All right. Is there Menti?
Yes.
Okay.
There is Menti to refresh us a little bit. So I believe, let me also confirm, head over to Menti, the browser window, if you haven't closed it.
Yeah, I'm trying to confirm myself.
I'm going to start it. Then you'll just be navigated to it. Yes. We have 75, 76.
Oops.
Let's get to 100 and I can start it off. Okay, just in case.
Yes. So please, if you want to join, use the QR code.
2 more. Okay, so I'm going to start it. This one is easier. Which of the following is true about the size of the base IPv6 header? Yeah, you can see already 29, 30. So is it variable from 20 to 60 bytes? Is it 20 bytes fixed? 40 bytes fixed? Variable 40 to 60 bytes. This one, all of them should get it right, right?
Very easy, I believe.
Most of them got it right, but some,
yes.
maybe you can explain.
So, all right. So yes, I did mention, maybe I said it too fast, that you have the IPv4 header varies between 20 to 60 bytes. It's not a fixed header byte there for IPv4, and that's why you have the IHL field that was removed, not replaced. I mean, that was eliminated, sorry. Now, 20 bytes fixed, that is definitely wrong. I don't know what protocol has that. That is wrong. And then variable 40 to 60 bytes also. So what's it called? IPv6 has that fixed 40 bytes, which is the correct answer you have there with 57. But any additional, field or additions that introduce additional byte fields that have been removed out of the base header, okay? And that's why I said one of the reasons why it's more than just a huge address space. There are other features we'll see next week, but one of them is this fixed header byte size that it's much more efficient to process for IPv6 nodes.
Okay. So the leaderboard. Yeah, Robert is still at the top. Tim, Daniel, and I can't see the fourth one. Yeah, and Matthew. So anything that we can sort out quickly before we look at the last section? Tesfire is asking this in the chat. It's in the chat. How to handle broadcast feature in IPv6. There's no broadcast in IPv6, right? It was completely removed. Of course, if you look at FF02::1, it's sort of like broadcast, right? Because you're going to send traffic to all nodes in the link, right? But for most of the part, if you want to do specific things, you don't send traffic to everyone. You send traffic using, we'll look at this next week, as we've been mentioning, the neighbor solicitation, neighbor advertisements, using specific multicast groups with including the solicited node multicast groups that we've been talking about. Q&A, I think is okay, right? Proceed. I'll look at it later. Yeah, it looks okay. Okay, so finally, this is a section that we look at in terms of basic configuration. So I'll just highlight a quick review of basic configuration on major platforms. So if you look at IPv6 support, we are in the year 2024, right? So unless you're using old equipment, which probably happens, right? Some people have not yet upgraded or done a refresh of the devices. Unless you're using very old equipment, your device most likely supports IPv6. And again, we'll look at this later. Just because you can configure an address on the device doesn't mean it supports IPv6. If it's a router, it needs to do the same thing that you're doing in IPv4. If it's OSPF, it needs to support OSPF v3. But most operating systems have IPv6 support. So in terms of configuration, in Windows, it's pretty much the same. I know this slide is from way back, but the process is the same, right? Navigate to your settings, control panel, and then interface settings, IPv6, then enter an address manually or automatically. Again, next week, we'll talk about automatic address provisioning. On macOS, same thing. Go to the settings, and then you can specify whether the address is configured manually or automatically. And if it's manually, you enter the address. And if it's automatically, the relevant provisioning mechanism will be implemented, and you'll be issued with an address. So on Linux, if you're configuring v6, you have net plan. And so this is an example of how you will do it. If you want to enable IPv6, so first of all, you need to edit the interface configuration under the net plan. We have a file there, a .yaml file. And then inside that file, you specify whether you want to do GetPv6 or if you're doing a static IPv6 address allocation and the name servers at the bottom. So of course, we'll share the slides and you can look at this in detail. Same thing on Cisco. If you work on Cisco, these are the procedures that you'll use to configure basic IPv6 on an interface. You enable IPv6, enter the address, the prefix length, and whether you want to use EY64 on the interface as the last 64 bits. And then for static, same thing. You can even specify if it's a linked local address that you're configuring statically. For Cisco, you also need to enable IPv6 unicast routing. We look at this on the last week when you're talking about routing, right? Okay. If you're enabling routing on IPv6 on a router. Same thing with Junos. You edit the interface, then enter the interface name, enter the address, and set the INET6 address family. So in terms of troubleshooting, I'll also go through this quickly because we'll share the slides, right? But what you need to know is we have similar commands to do the troubleshooting. So in Linux, for v4, you most likely been using the ping, right? For v6, ping 6. Traceroute 6. ifconfig is still ifconfig. Then to view the routing table, use the netstat command. The only difference is in v4 on the right, it's inet and inet6 in IPv6. If you want to see the neighbor table, this is the command, and the neighbor table in IPv6 in IPv4 on the right, basically ARP, right? Same thing applies to macOS. You have the versions, the commands you use in IPv4 and IPv6. Windows, the same thing. So ping IPv4 and ping IPv6. So basically we have equivalents of IPv6 commands to what we do in IPv4. So at this point, we're at the end. Let's check. Let me see if there's any pending question in the Q&A. I think most of this we answered. The difference between eliminated and removed. What is the range of unicast addresses? So it depends. If it's a global unicast, we have the range 200::/3. That means we can start from 200::/3 up to 3FFF. Is something else? Is FF00::1 the same as FF:1? No, it's not the same. I think this is in relation to suppressing, compressing. So FF00::1 is not the same. If you expand it in full, FF00::1 it will be FF00:0:0:0 6 groups, and then 001. So listed, I think we've talked about listed node multicast, right? Mm-hmm. And next week we'll look at listed node multicast in depth. Wongani was asking why don't we have broadcast IPv6 addresses? We've mentioned this, right?
Why do you want to have broadcast IPv6 addresses?
So it's to reduce the noise on the link, right? That's why we use multicast. And then solicited address used, we've answered this. And for solicited node multicast, it's one of those topics that are usually challenging the first time you encounter it. And that's why we have this introductory section. Then next week, when we talk about neighbor discovery, we'll revisit it again.
Okay, so some people have raised their hands. Labi, you want to talk again? Let's see. You can. Okay, raise the lower the hands. Good. So Abdul Hakim.
Thank you so much, Bashir and our colleague. My name is Abdul Hakim Warsame from Mogadishu, Somalia. We had a lot of difficulties for the last 3 days. Our bottle academic, but today at least we relaxed. So please, for preparation for the next week, Wednesday, can we get for some notes or these slides to prepare ourselves for readings?
Okay, so at the end of, okay, thank you for that question. So at the end of this workshop, we're going to wait for the recording to process, and you will get, all of you in attendance, you will get an email with the link to the YouTube, unlisted video on YouTube for this recording for your review, for review purposes. Also, in that email will be the PDF version of the slides that we're using in this presentation, okay? So you
Thank
say,
you so much.
okay, all right.
Thank you so much. I appreciate it. And I would like to say everybody, good afternoon.
Good afternoon to you too. Thank you very much. Let's see. Michael still wants to talk. So Michael, you can talk. Michael's yeah.
Hello.
Yes, Michael, we can hear you.
Good afternoon from Nigeria.
Good afternoon, sir.
Yes, sir. I still want to find out, are we still going to be able to combine the online and this one together? Because the online, you can go at your pace, but this times we have to attend to some things and other things. So I don't know. Are we still going to have the online course back combined with this Zoom session?
Okay, so I don't know if you you got the email about asking you for feedback yesterday, which session you wanted, the format you
yes, I
for.
got it.
Okay, so I don't know what you voted for. You don't have to say here, but
I voted for this Zoom session.
I see.
But with the understanding that you'll be able to work on the slowness of the site. So I don't know.
So yes, as you can see, it has the site is under maintenance right now. So because we are working round the clock to try to bring that thing back up, and then you can use it to supplement your this new format we've just created now.
Exactly.
So but hopefully, we're still waiting. I can't give you a time frame. Hopefully this will be sorted soon. Like I said, it's for you to, like I said, to supplement what you are doing right now. But in the meantime, we have to follow this format. All right. Yeah. So if you remember, the other option for the survey was to wait for the next cohort where you'll be automatically enrolled. You don't have to, you just be automatically for the next one when we've sorted out everything and we start over again.
Okay, thank you very much.
You're welcome, sir. There's Tiki, if I come right to Tiki Kill. Okay. I can talk if you want. You want to talk? Okay. That's Patrick.
Hello, good afternoon.
Good afternoon, Patrick.
I quite appreciate this class, and I want to say thank you to our facilitators. but I came in a little bit late into the session, and there was a point we were talking about the compression and the suppression of those 00s. So I totally missed that part. Are you saying we can't suppress the later zeros, the ones that are after the dot, the colon? Is it the ones before that we can only suppress, and we cannot suppress the ones after?
Yes. So okay, maybe so when the suppression rule is that you can only suppress, I say suppress. So I'm hungry.
Sorry about that.
You can suppress is they are the leading zeros. You can't suppress a zero after a numeral that is not zero, or hexadecimal digit that is not zero. So for example, what Bashir is writing, we wrote there now 0100, that one you see there. You can only suppress that particular leading zero, the one before the one. But the zeros after that one cannot be, you can't touch them. All right. So that's the suppression. You suppress leading zeros.
Oh, great.
So that means the zero to the left. Before a hexadecimal digit that is not zero.
So all the ones that are all zeros can be fully suppressed.
Yes, you can. All zeros can be compressed, or you can suppress them also if you want.
Okay, fantastic. Thank you so much.
All right, thank you. There's Samuel here. I don't know if Samuel wants to talk.
Yeah. Can you hear me?
Yes, I can hear you. That's fine.
Yeah, I wanted to know about next week's agenda. Could you please provide us like the topics so we prepare in advance? So when you do the live session next week, all of us should be on the same page.
Okay, yeah, that's a very good question. Thank you for that. So I answered one of them because someone did mention in the Q&A asking that where will they get a calendar? And I said the calendar will be updated today. So in that email you got yesterday, I don't know if you got the email. There's going to be, sorry?
I did get the email yesterday. I did.
Yes, there was a bit of a breakdown there.
It.
Yes, there was a breakdown with the time zones where you have, so next week, Wednesday, we're going to do the IPv6 address planning. That's just the only topic we're going to do next week, Wednesday. And then on Friday, we're going to do mastering IPv6 neighbor discovery protocol and provision IPv6 address config, sorry, config. All right, on Friday, that is 27 or so, correct? Yeah. And then the Wednesday after that is going to be routing, IPv6 routing. And don't worry, I'm going to give you the calendar. I'm just saying it off the top of my head. It's going to be IPv6 routing. That's Wednesday. I can't remember. It's in October, if I'm correct. Maybe October 2nd or something. It's going to be, yeah.
Routing
and transition mechanisms part 1, because that one is very long. So it's good. You're going to take a bit of that. And then on Friday, the third week, this is the first week we are. And Friday, the third week, is going to be all transition mechanisms.
Okay, thank you. But what I'm referring to is, could you break down the topics? Like, let's say, for example, you include Anycast, Madcast, and things like those. So we know, okay, at some point, we'll talk about Madcast. At some point, we'll talk about Anycast. At some point, we'll talk about Unicast. Such things. Not necessarily in details, but the main small topics.
Okay, so when the calendar is updated, because if you looked at the group calendar before we shut down the site for maintenance, you see that there was the breakdown. So we're going to update the calendar again. So IPv6 create the perfect IPv6 address plan, for example, is going to have all the lessons under it listed. So it's not just that broad topic, but the subtopics under it and what you can focus on for that session. I don't know if that helps.
Yeah. Yeah, thank you.
Thank you.
Thank you so much.
You're welcome. I don't know if Olumide Olatunji still wants to talk. Let's see. There you go. Let me, they are unmuted, but you're not talking. Okay, so I don't see questions on the schedule already. Thank you. So there's recommended textbooks. All right, for I see. Already available. But one of the very, I mean, my own opinion, one of the good textbooks, because you can't have one source of one definitive source of information for any topic or concept. I learned that a long time ago. But a good place to start is IPv6 Fundamentals. I think this is the second edition now by Rick Graziani, if I pronounce that correctly. Okay.
Yeah, but we'll also share the slides. And
let's share the
hopefully
slides.
it will help. So I think I still have the leaderboard
Yes,
to show.
you need to share
then
a little bit.
you have a survey, right?
Yes.
Okay. So before we leave, we'll just look at the leaderboard. Then we'll reach out to, we'll send you an email. So that's the current leaderboard and the top 5. So good job to Robert. And it was very close since we need to be answering the question fast. So top 5 will provide you a chance or sponsorship for the silver exam. And all I will send you.
Yeah.
Reach out to you.
All right. Let me. So before we see discussion. Before we end this session, so there's going to be just a quick survey, very quick. All right. So see right there on your screen, there's a QR code. You can scan it if you want, or you can go to that shortened URL link and just fill in the survey. It's very short, 2 minutes max. Just to we want to see how what you think about the session, and then we can use your feedback to improve upcoming sessions. So you can scan the QR code and just take the survey, or go to bit.ly/ls-1-0920. So I see 53 of you are there. All right now. 7 of you. No, 67, sorry.
Robert, it's okay. Yeah, 76.
Yeah.
So please help us with your feedback. We have a few seconds left. To help us to tailor this for you, right? And also for us to improve. Yeah, so Ronald is telling Robert to get another phone.
All right, I see the yellow circle. It's about to complete its animation. So there we go. All right. I think timer is up. You can still feel it anyway, but so again, I would like to thank you all. How many of you here now? Over 141 of you who showed up today and have, weathered the storm with us concerning the technical challenges we've been experiencing. And thank you for your questions. Thank you for your interest in this online cohort. And as I said, you'll be getting a recording of this session with the PDF versions of the slide. In that communication also, there'll be an updated calendar, the Google Calendar with the details of the upcoming sessions. So with that said, and then also the top 5, I can't remember who was the first anymore, but we'll look at the records. You're getting communications also regarding the discount vouchers you're going to get. So with that said, I would like to thank you all again for attending this session, and we look forward to seeing you on Wednesday, all right? From our end here in Mauritius, we wish you a very good evening, all right? You take care, and we'll see you on Wednesday. Thank you.